Okay, so this month we'll focus on the two major copper deposits type. Today in our both sessions we'll bring you the sediment-hosted copper deposits in our new formats. So we'll have 2 to 3 talks and 1 discussion. This morning we'll focus on basinal and structural controls of these deposits, while in the afternoon, and I am taking this chance to invite you to join to hear about the geochemical perspectives. So to start these sessions, I have the pleasure to introduce one of our specialists on sediment-hosted copper deposits, Dave Selley. Dave Selley is a senior researcher at CODES. His research focuses on the intimate relations between structural, sedimentological, and magmatic evolution of basins and formation of giant ore deposits. He has led major multidisciplinary research projects on the Central African Copperbelt and has held senior technical roles in the minerals industry. So Dave, the floor is yours in the next 15 minutes.
Thanks very much, Filipa. And to everybody else who's joining us for what I hope is going to be a stimulating discussion. So as the first cab off the rank, I've been tasked with providing an overview of sediment-hosted copper and the Copperbelt in general, but and hopefully that's going to provide us with a basis for today's discussions. But I do confess that I have assumed that you've done at least some basic homework, and that I don't have to tell you that these systems form from interaction of oxidizing hematite stable saline ore fluids with an in situ reservoir of reduced sulfur, or the Copperbelt is hosted in a Neo-Proterozoic failed reef that closed at 500 million years. These sort of basic things I'm taken as a given, and instead what I'd like to present, mainly in a sort of philosophical approach as opposed to presenting hard data, is some of the aspects of the ore forming process on the Copperbelt and applicable to other systems that keep me awake at night, and specifically how well do we understand the hydrologic evolution of these systems, because in essence it's this understanding that allows us to build robust and predictive exploration models. Are we there yet? I don't think so. This is partly because of the fragmentary nature of the data sets, particularly at the basin scale. But what I'm hoping to demonstrate, along with Koen today, is that we're on the right path. So what are some of the deposit scale constraints that we have? Just going to excuse me for a minute while I turn on my laser pointer. And it's been recognised from a very early stage that we have a relatively simple hydrologic and a redox architecture that's applicable to many of the Copperbelt deposits, and indeed many systems worldwide. So in this cartoon up on the top left, we're looking at a figure here from Garlic as far back as 1961, which describes the configuration of the Chambishi deposit. This is one of the Zambian Copperbelt deposits in a very schematic sense, but it basically shows the ores positioned at the base of a reducing element. Here's our redox interface here, transgressing an underlying footwall aquifer, coarse grain material with a distinctive laterally tapering geometry. So pinching out onto what's known colloquially as a basement high. So a spatial association of ores with basement highs. It's long been recognised. So passage of ore-bearing brine through the basal coarse-grained aquifer towards the redox interface. And we now understand that this configuration occurs at a very specific stage of rift evolution, a transition from an early synrift a phase in which we accumulate coarse-grained subaerial material within a series of disconnected depot centres. And then we hit a rift climax, and there's a fundamental change in the controlling fault architecture. We abandon many of the faults, and we subside the basin floor and we blanket these early compartments by a marginal marine association. It's not rocket science, but it's understanding the nature of the basin configuration across this transition provides us with a pretty powerful exploration tool. And where we've got relatively high density drilling, and indeed in the very rare cases where we have reasonable outcrop, we can describe this configuration in map view. And that's what's demonstrated here on the right. Here we're looking at a very simplified map of the Ekandjo system. It's again one of the Zambian Copperbelt deposits. Indeed, it's the largest deposit on the Copperbelt, showing basement here in the grey. This is the unconformity with the overlying rift sequence, and we can see very well constrained here is this beautiful ornate surface through here, these numerous little perturbations, promontories, re-entrants. These combined with thickness variation within the syn rift sequence allows us to define early form syn rift compartments, okay, separated by our basement highs or our zones of relatively limited accommodation development. So the ores, they're shown here as surface projection in map view. We can also see them here in profile. A number of them are sitting very close to the level of the ore shale. So that's shown here in this black line. And we can see that in many cases, they're positioned towards the margins of these early syn rift aquifers. So that's pretty nice. What happens if we don't have high density drilling, or if we've stepped away from areas of exposed basement? And indeed, that's the exploration space that we've moved into now, the relatively mature exploration space on the Copperbelt. Here we've got to start to use indirect methods. So we've got to use proxies. And they may include using the geometry of orogenic fold patterns as a proxy for early rift architecture, various geophysical tools, surface geochemistry. They all provide insight, but they have their limitations. And we really have to concede that, at least regionally, we have only very vague constraints on the aquifer geometry. And then, of course, we have deposits that don't conform to this simple hydrological model, and Kamoa-Kakula and Kansanshi are systems which come to mind. They're very large systems, very different in terms of their style, but they're great prizes. So much so that the operators there have drilled very deep into the footwall stratigraphy in an attempt to constrain the aquifer geometry. And when I mean deep, I mean pretty damn deep here. I mean, some of these holes here are drilled to nearly 2 kilometres below the level of the redox interface, but they failed to intersect basement. So in these systems here, we're dealing with an unusually thick footwall aquifer system. Okay, this profile, as it says here, is Kamoa-Kakula. This is one of the largest of the Congolese deposits in the far northwestern arm of the Copperbelt. And we're looking at offensive profiles from Kennedy and others in 2016 from south through to north over a lateral distance of something like 30 kilometres. And we can see macroscopically that there are some significant thickness variations in this footwall aquifer. And indeed, as we come to the north, we're in a very condensed sequence. So we've come out onto the basin margin here. But the real prize here is Kakula. Okay, this is at the far southern end of this profile. In fact, it's 10 kilometres beyond the edge of this profile. So it's 30 kilometres beyond the limit of the basin's edge. So how do we explore for this style of deposit, particularly if we're dealing with a blind deposit, which actually is the case for Kakula? What we do know about the broader Kamoa-Kakula system is that the distribution of mineralisation is strongly controlled by the availability of reduced sulphur once we step across this redox interface. And indeed at Kakula, which contains something like 20 million tonnes of contained copper, The bulk of the resource is contained within a sulfidic siltstone positioned right on the redox interface, and it's contained within a very narrow and very, very subtle graben. It's hardly recognisable at the macro scale. And we have several lines of evidence, which unfortunately I can't present in this forum, but they indicate that also contributing to the localisation of mineralisation is leakage along the margin of this graben. So vertical leakage through the redox interface and into the hanging wall. So in addition to understanding the hydrological architecture of the footwall, we must also consider the permeability meshwork at and above the level of mineralisation. And again, this is a feature which has been long suspected in the classical deposits of the Zambian Copperbelt, where we see a relatively systematic association between metal tenor and facies variation at the level of the ore, so within the ore shale, that suggests that primary permeability has influenced fluid flux. So here we're looking at an unrolled profile. We're looking basically down onto the ore shale of the Ekandjo system. We're going to look at this in quite a bit more detail in Koen's talk. Another large system, 18 kilometres in strike length. And the tenor of mineralisation, or the quality of ore, is expressed here by showing the zonation of the dominant sulphide species. So the highest grade is in the bornite zone, and then we progressively drop off grade as we start to increase chalcopyrite, and then to the right-hand side of the system, chalcopyrite, and then ultimately pyrite becomes dominant. In the background to this zonation, we're looking at facies variation of the ore shale, and there's 4 facies variants, 2 of which are barren. They're known as barren gaps. In the orange here are small arenaceous barren gaps or sandy fans occurring here on the left-hand side of the diagram. And then in the blue are dolomitic barren gaps. These are effectively biothermal patcheries. The vast majority of the resource is contained within what's known as the dolomitic siltstone facies, so a relatively coarse-grained facies variant containing numerous thin sandy intervals, and this transitions southward into a much finer grained unit known as the carbonaceous shale facies, which has an antithetic relationship with high-grade mineralisation. The grade always drops off as we step into the carbonaceous facies. So here, clearly we're not dealing with a reductant limited system. The distribution of ore is apparently linked to permeability at the level of mineralisation. And indeed, we can see here that the facies variation is basically just showing us sediment input or sediment dispersal patterns. So the dolomitic siltstone facies is basically forming an apron to our points of sediment input, which are shown here by these arenaceous fans, whereas to the right-hand side of the diagram, we've moved into a starved part of the basin. Okay, sediment supply in part limited by these barrier reefs. So a spatial association of high-grade ore with the margins of these relatively permeable arenaceous barren gaps. So a slight variation on this theme is shown by the next deposit to the north. This is Chambishi southeast. And we're looking in map view of thickness variation of the footwall aquifer. So the hotter colours, they're thicker parts of the sequence, and then progressively pinching out towards zero with the cooler colours. The controlling structures here, west-northwest to northwest in orientation, they interfere in this central zone. We've got a little transfer zone or relay ramp configuration where we have one of our basement highs. Okay, and we can see around the margins of this basement high, we've got all of these little ornate re-entrants of relatively condensed footwall material. We overlie the facies variation at the level of the ore shale, and we can see our barren gaps here, dolomitic barren gap positioned above these pre-existing basement highs, and the arenaceous barren gaps are our sandy fans being fed through breaks in the fault system. We have an apron of dolomitic siltstone facies and then out towards the southwest into the carbonaceous shale facies. We overlay the distribution of ore and we can see quite clearly that the thickest and highest grade parts of the ore body occur where there is a vertical coincidence of the lateral pinch outs of the footwall aquifer and zones of enhanced permeability at the level of ore. Okay, so this geometry, or this is pretty much encapsulated in this model here on the right of a transfer zone. Transfer zones are zones of relatively limited accommodation development. So we're seeing pinch out at the lower aquifer. There are also sites of sediment input. So these are zones of relatively coarse grain material. So permeability at the level of mineralization. So transfer zones are good. But yet, again, there are exceptions to the rule, and it's in Changa. We come back to that, and this is a bit of a fly in the ointment, because in Changa, ores are at least partly hosted within the relatively tight carbonaceous ore shale facies. Now, I must confess that I've never worked on this deposit, and I haven't seen the ores for something like 20 years. So this is based largely on published literature, but my understanding is that a significant component of the resource is contained within that relatively impermeable carbonaceous ore shale facies. And it tends to suggest that if we have sufficient fluid flux, we can drive the fluids through, even through relatively impermeable media. If we have a look at this section in a bit more detail, we can see that there's additional complications. So here at Nchanga, remembering that this is the position of the ore shale, we can see that at least part of the ores are superimposed on the carbonaceous ore shale facies. But as we shift southwards to Chingola, we can see that the ore bodies progressively step off this interface and they're entirely contained within the relatively permeable footwall where they're replacing former hydrocarbon trap sites. But the ore shale itself is unmineralized. It dies out further to the south, that's this dotted line, and then it reappears a bit further to the south where again we have footwall ore bodies in the permeable sandstones, but the ore shale is pyritic and effectively barren. And this tends to suggest here that we've got lateral compartmentalisation from a hydrologic perspective. High fluid fluxes in this region here, around Nchanga, the system progressively waning or dying off as we shift to the south. We step out again. This is the previous map, Nchanga and Chingola to the south. I do apologise here for the coarseness of the map we're going to have to work with. There's lots of lovely proprietary data sets, but in this forum we're just going to have to deal with the survey maps here, but they should be sufficient for the point that I'm trying to make. The basement is shown here in the red and the green. We've got another couple of inliers here to the south. The rift material is shown in the yellow. This is the aquifer and host sequence. And there doesn't appear to be significant variation as we shift to the south compared to the Nchanga domain. There's arguably some increase in thickness, but a lot of this is apparent and related to variation in bedding depth. What I want to draw your attention to is this upper level of the stratigraphy, which is shown here in the blue. This is the evaporitic level of the stratigraphy. Fragmental carbonates, breccias after former concentrations of salt, as well as these numerous small bodies of mafic material, which is shown here in the green. And we can see that this facies association is either considerably thinner or largely absent as we shift northward to the fringe of the Nchanga domain. So we've got a very important change in basin architecture, not at the level of mineralization or in the footwall, but within the hanging wall as we shift towards the south. Okay, and arguably we have a thicker and less permeable evaporitic stratigraphy forming the hanging wall in this region. Important just to re-emphasize that as we step across the linear through here, across this fundamental sub-basin margin, we do see locally the ore shale persisting to the south. It's carbonaceous facies, but it's ubiquitously barren and pyritic. Okay, so it's suggesting here that we really need to understand the permeability meshwork at high levels of the stratigraphy, way up into the hanging wall, and that's potentially playing an equally important role to the hydrological architecture deeper in the profile. How wide do we have to go? Well, arguably to the basin scale. So on the right here, we're looking at the distribution of the various ores of the Copperbelt, highly varied in terms of their stratigraphic position, their style, their metal association, as well as their timing. But the vast majority of these ores, certainly the largest of these ores, occur towards the fringe or outboard of a salt-bearing depot centre, which is highlighted here in this red dotted line. Okay, the deposits that we've been talking about in Changa, Chambesi and Nkana are positioned here, arguably outboard of relatively thick salt. Kansanshi, we touched on very briefly, again, outboard of a relatively thick salt and occurring in an area known as Domes region. And then Kamoa-Kakula out here in the far northwest, where there is no evidence that there was any evaporites within the basin. We're dealing within a relatively coarse-grained clastic fringe to the basin. In the centre here, we're looking at stratigraphic profiles from the southeast, through to the northwest. At the peripheries of the basin, in the southeast and the northwest, we can see that we're dealing with anomalously condensed stratigraphy. The thickest part of the profile occurs here within a depot centre maximum in the centre of the basin once we've stepped here into Congo. From a stratigraphic perspective, the ores are partly contained within, but mainly form a fringe to this blue compartment. This is evaporitic stratigraphy. Relatively thick salt originally accumulated within the central part of the basin. It became modified into diapirs and then becoming progressively attenuated as we shift towards the basin margin. And the role of the salt here is twofold from a hydrologic perspective. Firstly, whilst it's intact, it's impermeable, okay? So it forms a seal to this underlying aquifer system, okay? Secondly, it generates ore fluid. During its deposition, it forms a residual brine, which is anomalously dense. It sinks down into the underlying aquifer system. It displaces the less dense connate brines, and we start to generate convection, okay? As long as the salt here remains intact, this lower compartment is effectively protected from dilution, and there is no fluid egress to high levels of the stratigraphy. At more advanced stages of basin development, we start to see modification of the evaporitic stratigraphy, in part through halokinesis, so withdrawal of salt, locally dissolution of salt, or structural modification of the seal as we shift towards the margins of the basin. So at advanced stages of basin development, these marginal zones start to become leaky, and we start to expel fluids from our deep-seated aquifer. So it's not surprising then that the largest of our systems occur towards the periphery of the basin and outboard of relatively thick salt. So the biggest systems here are Kamoa, Kolwezi, Tenke, Fungarumi, in the Congo, in Changa, Konkola, and Nkana here to the south. So I've got in a little slide pack here a number of images that sort of illustrate the kind of breaching of that evaporitic seal that may occur at the deposit scale. I'm going to sort of say those later, that we might be using those in the discussion, but I'm going to finish off the main part of the presentation just with a view of some fluid flow modelling. Now, it's quite sophisticated mathematics, but it's very simple geologically, and it's certainly not the truth. but it does provide us with some insight to the kind of processes which are permissible within this environment. So it's a model that ran for, I think, about 150 million years dynamically. So we dynamically subsided the basement, which is shown here in pink, and accumulated a rift sequence, including a laterally taping aquifer, which is shown here in the orange. And we've overlain that with relatively impermeable salt. And the upper layer of salt here extends basin-wide. As I pointed out, this forms a seal, but it also it generates our ore. So as we deposited this salt, we've introduced a dense brine into the underlying aquifer. The passage of this brine is tracked here by these little circles. These are little tracer particles. We can see that some of these have extended down into basement, but most of the action here is within the aquifer. And you can see here by the curvilinear trace of these particles that they're starting to define here convective cells. And the convection here is driven entirely by thermal buoyancy. So the thermal contrast between the thicker parts of the basin, where it's relatively hot, and the cooler marginal parts of the basin. On the right-hand side of the diagram, at the same time, this is at about 120 million years, we're looking at the time integrated fluid flux. The dark blue zones are the impermeable salt. Okay, so I'll highlight those. But we can see here that the highest fluid fluxes occur in this hinge position, okay, where the aquifer is starting to pinch out, and particularly on the immediate margin of salt. And there's a number of reasons for this, but one of them is that because we've breached the salt at this position here, and this has allowed small-scale convective cells to develop within this hinged position here. Out towards the left-hand side of the diagram, there's conspicuously low fluid flux, and this is somewhat artificial. It's an artifact of the model, and that's because we've got closed boundaries. So this boundary here is closed, and as I pointed out, this upper layer of salt is basin-wide, so it produces a cap. So the fluids at this position here are effectively trapped. So we can see here there's a dense bunching of particles, but effectively the system here is stagnant. Okay, we've got no throughput of fluids in here. We've got anomalously high fluid pressures, which is important because it allows maintenance of porosity and permeability at very advanced stages of the model. So this is still, at least within the aquifer system, we're dealing with relatively high permeabilities. We may see some mineralization at the redox interface, but unless we breach this overlying cap, we have no fluid throughput and we're unlikely to generate ore. So we have this unusual situation where we may have an intensely altered aquifer developed over a huge distance, but relatively limited mineralization. What happens when we breach the seal? Well, we have a very massive but very short-lived period of high velocity fluid discharge. So we've done this by breaching the seal at this point here. Is it 140 million years? And then within 10 to 20,000 years, we have this very, very significant high velocity discharge. What happens after the discharge event and we depressurize the aquifer, we start to collapse porosity and the system starts to shut down. We can see that we've got relatively weak convection still occurring here, but we can see by the size of the velocity vectors that the system is effectively shut down. So that's where I want to leave it for this little introduction, just to highlight the fact here that it's not sufficient to really try and resolve the hydrological architecture at the deposit scale. We really have to understand what's happening at the basin scale and at numerous levels, both within the footwall, the level of mineralization, and up into the hanging wall. The hanging wall permeability meshwork is perhaps equally as important as what's happening down here deep within the basin. And because we're dealing here with a salt carapace, it's a highly dynamic setting, okay? And we can have a very complex and protracted evolution, hydrologic evolution, because salt quite literally is a movable feast. We can breach the salt at different parts of the basin at different times, leading to different styles of mineralization with quite different character. So I'll leave it at that. I've probably just used up my 15 minutes or close to 15 minutes. And do you want to just move on to the next person, Filipa? Or
yeah. Thank you, Dave. Yeah, we all go directly to Koen. Yeah, great. So our second speaker today is another specialist on our today's topic. Koen is a structural geologist who specializes in mineral deposits in sedimentary basins, and currently is an assistant professor at University College of Dublin. And at iCRAG, Koen research focus on analyzing structural and stratigraphic controls on mineral deposits at the regional and deposit scale. Currently is working on the Irish ore field, the Central African Copperbelt, and the Gharia Belt. So Koen, next 15 minutes is for you.
Perfect. Thanks, Filipa. I hope you can hear me well. So that was a very good introduction almost to what I'm going to talk about, and I'm going to kind of look for ties with Davy's presentation there. So hi, I'm Koen. I'm currently at UCD in Dublin, and just going to present a broad overview of some of the concepts that I think are important with regards to basin fluid flow and the control of structures on that, and then just end up with an example at the Enkana Shambishi Basin, just to illustrate how we could use that. So, I mean, Davy talked about this, and it's been published on what successful sediment-hosted stratiform copper provinces contain, and that is basically three basic tectonic and lithostratigraphic elements. It's continental red beds or permeable syn-rift sequences, reducing strata and evaporites that provide a seal. And Davy Selley basically touched upon all of those and different conceptual configurations in different parts of the Copperbelt. I'm going to focus on the Copperbelt as well, but these processes are presumably applicable to many other sediment-hosted copper provinces. So, you know, this sort of generalized figure from Murray Hitzman's paper in 2010 shows you a situation that is applicable to the Copperbelt, which is you have a syn-rift sequence with, you know, locally very thick red beds, kilometers of them, and then lateral fringes with pinch outs in a continental rift with on top of that, a sag phase of sedimentation, basically infilling most of this architecture. Some faults probably continue through later times, and then that's capped by evaporites and carbonates in a layer cake style. And then you've got further post-drift sequences. And so what I want to focus on is, suppose we have these elements in a world-class province like the Copperbelt, you know, then where do we find the higher grade mineralization? Part of that is trying to understand the chemical and hydrological architecture, which is not easy and requires observations across scales. And so when I'm talking across scales, this is a figure by Koen on sort of the processes, critical processes that I guess mineral exploration companies would be looking for when they're doing generative exploration, from, you know, identifying a new basin, identifying a play or a cluster of prospects, and then down to the prospect scale where you would go into identifying new areas of prospective mineralization. And so I wanted to focus on what we've been talking about here, is the architecture. I want to focus on fluid flow. What are the seals? What are the, you know, fluid flow pathways that you can get, and how does that get into the permeable rock rocks that you need and the reductants that are needed to find these deposits. And so it's really a multi-scale problem, and that's really the thesis of my talk is we're looking at the basin scale down to basically almost tens of meters scale, and I'm going to illustrate that. And so the real question that everyone's struggling with is when are the fluids produced? Because if you produce your fluids too early or too late, then obviously that will affect your ability to get them into the right units. And also when and how are they moving in basins? It's sort of this quote from Camp's paper, I think summarizes it a bit. So the real question is, how can we map the hydrodynamic behavior of basins through time? So it's thinking about this time element. And this is something that the petroleum industry is really good at, or has been good at, throughout many decades, with bigger cash pockets in a way, and different techniques they use. But how can we apply some of those techniques maybe across scales in our basis? And just I want to focus on the influence of faults on fluid flow. And this is a review paper published 2 years ago now, 2.5 years, talking about fault controlled fluid flow within extensional basins. So just a figure from that, this is the North Sea basin, or an area in the North Sea in the late Jurassic top turbid horizon. And what you can see here is, it's basically 10 kilometers by 10 or so of a permeable horizon, which is a reservoir horizon. There's 2 wells here, and you can see there's different faults that sort of die out along strike, and they transfer displacement across. So you can get a sense of the architecture of the horizon and the structures. But when you look at a cross section across it, it looks a bit like this, with lots of horse and grabens across this. And the important thing here is, a touch upon what Davey talked about as well, is pressure, fluid flow. And this is at the basin scale, can be governed by fluid pressure compartmentalisation. And this is governed by the way the faults and the fault blocks move and are juxtaposed to each other, how deep they are buried at a given time, how much sediment is on top of it, etc. And so what you can get in these basins, syn-drift and early post-drift, late post-drift, is huge pressure differences across faults. And you might not expect this, because sometimes people think that faults are only conduits for flow, but they can be baffles to flow at the same time. And so just to highlight that you can get 150 bars of pressure difference across a very small area, basically one fault zone. And you'll also note on this figure that there's a relay zone here, and these are areas where you could potentially breach or have fluid flow occurring. So there's distinct spots where this happens. And this is a figure by Tom Manzaki at University College Dublin, did some fluid flow modeling across. I just get my videos away here. So across a conceptual permeability network, you have just a 500 meter by 500 meter by 80 meter package with a lot of vertical height exaggeration, so the layers are kind of blown up to give you a better sense of what's happening. And there's 20 meter throw across this fault system. And so what you have is a relay ramp system, a fault complexity, and this can be any type of fault complexity, but for the purpose of that modeling, it was just a relay ramp. And what you can see is, when you do fluid flow modeling, I just want you to pay attention on the scale of what's happening when you do pressure drawdown from a producer injector well. And this is the type of work that people in the oil and gas industry do. So just the scale of this, right? So you're talking about, in all the permeable horizons across a fault, with just 20 meters displacement, you can get quite a bit of pressure drawdown and pressure differences occurring away from this. So it's around the scale of the model, hundreds of meters. And the fluid flow pathways are quite complex. And the streamlines of the flow paths show that there's fluid flow in every permeable layer in the model. And so this is maybe something that as mineral explorers, because we're dealing with dead systems essentially in terms of fluid flow, we don't really think about enough. And I just wanted to highlight that. And it also sort of highlights the roles of these connections, which at some point in time in basin history may or will have happened across fault systems. And so, you know, are we in fact conceptualizing faults the right way? And this is again work by fault analysis group in at UCD, looking at geometries of these fault systems. And so when we talk about relay ramps, we often, you know, see them as these idealized sections with a ramp like this. But in fact, you know, complexities along faults occur in many different shapes and forms. And this is just a figure to kind of illustrate this an analysis over many different basins where you have basically relay zones occurring in different geometries like this. And there's a whole range that you can get. And so these, as Davey talked about, these can impact local sediment. And then also the redox architecture and facies distribution. And then that's the question I have is about what are the expected scales? And so you could think about, you know, the amount of surface area along a fault. You do get a number of relay zones, even on relatively small faults. So let me dive straight in a 2-3 minutes or so in the Shambishi and Kana area, where Davey mentioned this. So this is the Sin Rift sequence overlain by the ore shale, which hosts most of the ore in this area. And so, you know, people have looked at the architecture in these basins, and so this is just in the Shambishi southeast area here, where we have, you know, some Sin Rift red sandstones, which in some cases could be quite thick. So this is obviously, to me, a basin bounding fault with significant amount of displacement. And then we go into the Sin Rift sequences. And this is where I think, and I want to put this forward for the discussion, where I think we should look for the answers, because we won't drill 2 or 3 kilometer holes to find, you know, the faults continuously. There's just no money to do that. And the seismic, reflection seismic doesn't always give us the answers. So it's really about the type of work that John Woodhead did, is looking at facies variability within the transition from Sin to sag facies to post drift in these basins. And yes, there are facies variabilities. We did some work around the Shambishi basin where we mapped out local facies variability. David talked about the carbonaceous facies, and then that transitioning into dolomitic or an argillaceous dolomite facies. And obviously that has an effect on the grade. It doesn't only have an effect on the grade, it also has an effect on the type of deformation, because you can imagine that a shale will deform quite differently than an argillaceous dolomite. And so we did a whole detailed structural analysis of different areas along the edge of this this outlier, essentially, with a difference between broad open folds occurring where you have the argillaceous dolomites, the more permeable architecture. When you go into transition into your carbonaceous facies, the folds get much tighter. You get hinge pinch outs, hinge parallel faulting, and a strong sense of non-cylindrical parasitic folding. And so this non-cylindrical parasitic folding, and I'll just skip to my last slide here, is essentially occurring at the scale of the faults. That's sort of the thesis I want to put forward. So when we compare, and this is a map by Dieter Brems, which I looked at again a few years later, with in red you have Mendola clastics, and then on top of that you've got your Copperbelt ore body member, and then you go into your post-drift sag facies, and the highest, so this is intensely folded, as you can see, and the folds have these types of geometries where you have non-cylindrical transfer of folding sort of illustrated here as well, and bifurcation. And what I think we can see is, and this is the map that Davy showed as well of the Shambishi southeast, which is not too far from this, is that when you look at the scale of the transfer zones in these areas, around, okay, well, a kilometer, well, this is 200 meters. So maybe we can use a combination of lithofacies, the deformation style, in these syn to post-drift transitions to actually elucidate what the hydrological architecture in these basins can be. And I'm going to leave it at that and go on to the discussion.
Okay, great, Koen. Thank you very much. So first, I would like to thank you both for bringing this really nice topic. And I am learning a lot. So we start having some questions, but before that, if you have any question to each other, I can give you the first word to Koen or Dave. Otherwise, we can go directly to audience questions. Okay, do you prefer that
I loved it. I thought it's great, and I think we're looking at it very similarly. The fundamental difference, obviously, is I'm placing a lot of emphasis on, I guess, the permeability meshwork above the level of mineralisation, up into that hanging wall sequence. Whereas you're focusing on the fault architecture at the level of mineralisation, which is clearly being overlooked in the presentation that I gave. And my feeling is that there's going to be elements of both of those, and the truth is going to be somewhere, I think, somewhere in between those. Mm-hmm. So I was very impressed. I think it's great.
There's a few questions in the chat. Thanks, David.
Yeah. I will start.
Yeah.
So, Philip Muches, if you want to unmute yourself and ask the question, please.
Yes, thank you very much, Filipa. Hi, Koen, and hi, Dave. Good to hear you and see you. I got a question for Dave. Dave, you mentioned in your talk that the Nchanga ore deposit was a little bit anomalous with regard to the other ones. What is the role of the shear zone in this deposit? Because it's a more complex setting for the different type of ore deposits, and there's variability between all the deposits. But what is the role of the shear zone identified in the high ore grade in Nchanga?
Yeah, okay. Well, I'm glad I did say that I've never worked on this deposit, so I'm giving myself a little bit of a way out here. Are you talking about the decoupling surface?
Yes, yes,
at the level of the ore shale.
Yes.
I
could provide the permeability.
Sorry, in terms of permeability, I've never worked on Nchanga, but there is, as far as I understand, a similar decoupling surface at the ore shale, particularly within the carbonaceous ore shale facies at Nkana in the south ore body. You do, as far as I understand, see a different style of alteration there, and there's evidence of a late phase of mineralisation. But as far as I understand, that is superimposed upon the pre-existing mineralisation. So the distribution of ore within the black shales in Nkana seems to be developed independently of that decoupling surface. But I'll leave it to Koen, who probably knows a lot more about that to expand upon.
Philippe does as well, because I think I may have the answers to some of that. Like, I haven't worked on Nchanga myself either, but you know, the carbonaceous shale facies, as you mentioned, is typically lower grade, but it is also much more deformed, and you do get a lot of accommodation space during the formation. I actually have a Bicky here because I've sort of anticipated that you know, it's not just basinal mineralization. This gets reworked, and you get maybe new inputs of mineralization, and some of the work that Filipa, I know, has shown that in terms of multi-phase mineralization pulses. So yeah, you can imagine these permeability pathways when you have shear zones or maybe a layer cake that gets deformed, that you can get these, funnels. So that's also a permeability architecture, which is maybe more synergenic. And clearly the ore, at least at the deposit scale, is being moved around a bit, because otherwise you wouldn't get the high grades in these carbonaceous shales.
Yeah, we didn't prepare this question, but thanks a lot, Koen. That's what I thought. It is that these zones provide an additional permeability during the orogeny, which caused indeed an enrichment or a new important mineralization. Thanks a lot.
Thank you, everyone. Halleluya.
Thanks, Koen and Debbie, for the great discussion. We have so many questions. I'm just going to jump on and ask Murray Hitzman to please unmute himself and he can ask his question.
So thanks a lot to both speakers. Fantastic talks. And I think what you both showed was scale is clearly incredibly important. And I guess from the just exploration perspective, how do we get the data to do these analyses? So in the areas where we have very detailed drilling, like Kamoa-Kakula, the Chambishi Basin, we can do it in various ways. How do we, in other areas, best use our geophysical and geochemical data to do the sort of structural hydrologic analysis that you guys presented? Thanks.
Yeah, I could talk maybe, and if you want, Davey. So I was just thinking about, obviously, there's new techniques that we're sort of borrowing from the petroleum industry, which is reflection seismic. There's been a lot of really detailed aeromag shot in the Copperbelt in particular. There's other geophysical techniques. What I think we're missing in the sequences is data on the petrophysics to really tie one-on-one, as in the geophysical scale to drill hole scale. And there's obviously sort of a lot of chemistry that you can do in terms of lithogeochemistry and the alteration patterns, but at a regional scale. It's often done at the deposit scale, but not pulled towards the regional scale. At least that's my impression. I don't know if that's what you think, Davey.
Yeah, I agree that there needs to be more work done with on the petrophysics. The seismic, from what I've seen, is not really been the silver bullet that everybody has hoped for, and I think you've touched on this before, and that's I think largely because there's not a lot of acoustic contrast between the lower part of the basin fill and the basement. So although there are some distinct reflectors internally within the stratigraphy, sometimes at the level of the ore, it's not been particularly effective in imaging the geometry of the deep-seated parts of the basin, which is obviously the great unknown. But I think as more surveys are done and we have a better understanding of how to apply that in the environment, in the Copperbelt environment, I think the products will become more enlightening. Yes, we've got a lot of sort of conventional magnetic and radiometric sort of potential field data sets. The magnetics is sort of near complete, but it's highly fragmentary and highly variable in terms of its level of resolution, and it's extremely difficult to interpret. At least I find that to be the case. When you're working on a particular snapshot or a postage stamp, it's a very powerful tool. But if we're trying to understand what's happening at the basin scale, I think we really need to have a stitched high resolution data set. I think the kind of work that First Quantum led and Scott Halley did in terms of the surface geochemistry really has changed our understanding of the scale of this hydrothermal system. A lot of the focus there was on mapping out mineralogical and chemical variations, which we think relate to the intensity fluid flux within the aquifer. But there's very little known about the geochemistry of the hanging wall of these sequence. I mean, there must be significant outflow through these deposits. Part of the problem is obviously many of these deposits are daylighting, meaning that the hanging wall or the outflow zone has been largely eroded. So we're limited in what we can tell about the upper levels of the ore system. But I think that's where there needs to be a greater focus. At the moment, most of it has been placed on the ore body themselves, the ore horizons themselves. We really need to step to higher levels of the stratigraphy in an attempt to map these outflows. As you know, my sort of bias is looking for breaches within the hanging wall stratigraphy. I think these are recognisable. Whether or not that can be done with geophysics alone, I'm not sure, but there are certainly areas where we can see where that seal is anomalously thin, and these commonly are associated with mineralisation. So I think doing the kind of work that you presented from John Woodhead, understanding the stratigraphic architecture of that higher level of the basin fill, I think is crucial. I don't know if that answered your question, Murray, but that's my bias.
Okay,
Thanks,
thank
Dave.
you. We have another question from Connor O'Sullivan. Do you want to unmute yourself, please?
Hi guys, great talk. Yeah, I was just wondering, Dave, you showed, I'm not quite sure like I'm a petroleum geologist by background, so I'm not sure the base modeling process you went through, but I was wondering, in the models where, particularly for your regionally extensive salt body, did you consider the thermal conductivity of having a fixed salt layer on the the net temperature in the subsalt basin at the time?
Yeah, that's a very interesting question, and I'd have to think back an awfully long way. I'm pretty sure that was included within the model, higher conductivity within the salt. Its effect, I think, if anything, was minimal, however.
Thanks.
Okay, Halleluya. We have a lot of questions here, so we'll continue.
We have a question from Hulk, and I just want to invite Hulk to our afternoon session because there'll be a lot of talks on the geochemistry part. I'm not sure if Koen and David wants to give this a go, but I'll read it out from Hulk. The question goes, are there any geochemical differences, especially for the pathfinder elements, during changing lithological units or along tectonic contacts? For example, are there critical differences in the elemental distribution of the ore zones in the sandstone, red bed contacts, or tectonic contacts? And the second part of that question is related to fluid pressure. How does the fluid pressure affect the grade or the quality of the ore? Dave, Koen?
On the second question, I could say it's not directly related at all. It's just that the fluid pressure just drives fluid flow, and then you have to take the architecture into account and how the fluid flow goes into that. So it's not directly related,
I think, well, actually, as part of the Miley Symposium, Daly and is it Tosca, I think, presented some interesting thermodynamic modelling. Now, I'm not sure about the veracity of this, but they looked at the concentration of copper within a metal-bearing fluid with the variables of temperature and pressure, dealing largely with relatively high temperatures of about 300 to 400 degrees. And they demonstrated that the capacity of the fluid to carry copper is dramatically increased with adiabatic decompression. So with a sudden reduction in fluid pressure, we dramatically increase, or potentially can dramatically increase, the concentration of metal within the ore fluid. So I think that's something that really has to be looked into further. It's something that we generally don't think about in this space.
Thanks,
Okay,
David.
great.
Hoke, please do join our afternoon session. I'm sure your question will be answered well in that session. Filipa, before I give it, maybe you would just like to ask ODS to unmute so they can ask a question. Okay, I can answer the question on the person's behalf. It says, what is the impact of bimodal volcanism, of volcanics heat component on the brine circulation?
Again, that's a very interesting topic, and one which we perhaps haven't given sufficient interest, attention to, because we know that the distribution of those very widespread but disconnected mafic bodies is quite patchy. There's some compartments where, as we showed in south of Inchanga, where we've got quite high volumes of mafic input, and certainly we'd expect to see higher geothermal gradients around those systems. There is actually an interesting association which I've never really fully understood in terms of alteration style, and that is when we have gabbroic bodies sitting very close or in the immediate hanging wall of mineralization, there's a transition from potassic dominated metasomatism to sodic metasomatism. And one possible explanation for the stabilization of albite over potassium feldspar is an increase in temperature. So I do wonder whether or not there is actually a thermal effect around some of these mafic bodies.
Okay, great. Before we move to other questions, I have to ask David and Koen, are you okay to stay more 5 to 10 minutes? The last questions?
Yes.
Okay.
No problem.
Okay, before that, Halleluya just post our link to certificate if you want to have a certificate from this session. So just click on the link and you will have a certificate of this session. So on behalf of David Plunkett, we have here a question. I will read it. So I think it's great you can find hints of these early perspective basin structures by using geology maps, showing later deformation as well as lithological units. I wonder if you could elaborate a bit more on this.
Well, I can say I think there's a direct relationship between the orogenic fold and thrust configuration and the early rift architecture. So I'm quite confident that you can use fold geometries as a proxy for rift architecture. That inheritance pattern is certainly there. What we're limited by is, I think, as Murray pointed out, the further we step away from the basin margin, we have less constraints from drilling, and our ability to really constrain the fold and fold architecture becomes limited, and we become almost entirely dependent on the geophysics. So again, it comes back to the necessity to develop seamless high-resolution geophysics to use this as an effective tool.
I agree. I fully agree. And what I would add to that maybe is that, you know, as the facies mapping in the Zambian Copperbelt shows is that you do have what seem to be highs. I don't think we really understand whether they are paleo highs and where the sort of, what the margin architecture of your Katanga basin looks like. And I think the combination of looking at the deformation, the deformation style that you see is probably a combination of both the fault architecture, especially around basin bounding faults, and paleo highs.
Thanks, Koen and Davey, for that. We have another question from John Wash, and I'd like to please ask John to unmute so you can ask your question. John, over to you.
If he's still here.
My question was just that obviously inversion along these faults is linked in part to the mineralization, and I wondered whether you get faults, basinal faults, which are not mineralized, whereas you get ones which are inverted, and the reason I ask that is because in my sort of experience, when you go from one basin to another, that inverted basins, the faults are much more localized in inversion. So it's only a subset of the original normal faults that are actually inverted. And that would sort of suggest that if inversion is inextricably linked to the actual mineralization, then there'll be lots of non-inverted faults, which won't be prospective, and there'll be fewer inverted faults, which are prospective. And I wondered whether those non-inverted faults exist.
I don't think people explore for the non-inverted faults. That's probably the answer there. So we just don't have the data maybe in this area. Well,
there is a sort of a chicken and egg in a way.
Yeah, I know.
Is that the faults you're most likely to see are the ones which are inverted, because it's the inversion which you're actually seeing rather than the original. So I wonder whether it's almost inevitable that the faults you're seeing are the ones which are inverted as opposed to those that aren't. But it's an interesting thing. I think it comes back to Davey's point that if we actually had seismic or we had imaging processes in which we could identify in the subsurface faults that aren't or weren't inverted, then we could actually test the importance of inversion and localization.
Yeah, I can't think of any faults which have not seen some level of inversion that I've seen. I mean, I've seen many faults which have preserved net normal displacement, but every structure that I've been able to recognise as an early fault has been inverted. And the other important thing to note here is that during the inversion phase, the entire basin is decoupled. So it's decoupled at the base of the salt. So the structures that we see, except when we're on the extreme limits of the basin, largely root into to that basal detachment at the lower level of the salt. So I would argue that there's a significant number of faults which are generated during inversion and new faults, but it's a relatively thin-skinned architecture that we're looking at.
Yeah, I suppose the salt is critical in all that, because if you don't have salt, obviously it's a thick-skinned system, and the basins we look at look to be much more lightly inverted rather than sort of newly formed. But if they're more often newly formed, then this coincidence between syn rift architecture and the later inversion shouldn't exist, or it should be less well defined. So I wonder, is that telling you it's more likely thick-skinned?
I guess it depends where you look, isn't it? In the Copperbelt, one place isn't like the other. So I mean, the areas that we looked at in the Zambian Copperbelt is, to use Davy's words, is on the margin of the basin. So when you go to the center of your basin, maybe it's different. And also, there's quite a lot of shortening. I don't know for sure what the numbers are, but it's quite a lot of shortening happening. So that obviously will also have an influence
It's hard to escape it.
Exactly. Yeah.
It is. I think we modeled something like 30% shortening on the regional sections, restored sections across the basin.
Yeah. Cool.
Okay, thank you, John.
Right.
We have another question from Victor. Do you want to unmute yourself?
Sure.
Thank
So
you.
my question is more directed to David. When you were showing this nice kind of ore shale facies transition diagram, you had this barren dolomitic gap in between two mineralized horizons, basically. So I mean, sure, it's less porous, I guess, but like, what is actually the driving fluid conduit for this? Are we looking at like faults that are bringing up the fluids, and that's like with a leakage into these more permeable, or why do we get this barren gap in between, basically?
Well, I probably should have mentioned that the barren gaps are reductant pore. If I didn't say that, that was an oversight on my part. So the arenaceous zones are strongly hematitic. There's fine-grained hematite, more akin to the kind of alteration that you see within the footwall aquifers, whereas the carbonates themselves are just strongly recrystallized. So the lack of mineralization there is principally reductant limited. But I mean, it comes back. We can see this intimate association between the quality of ore and facies variation. We know that the facies variation is linked to the early extensional architecture. So is it actually reflecting, as I think Koen would argue, that it's the role of the faults? It's the role of the fault. It just happens to be a happy coincidence that we're seeing facies variation linked to variations in ore tenor, but ultimately they link back to the same thing, to the controlling faults. So we're seeing greater fluid flux around the reactivated faults. So that's what's playing a critical role, rather than permeability variation or preservation of primary permeability within the ore shale itself. So I guess they're the two different ways of looking at it.
All right.
Okay, great. Any thoughts, Koen? That's fine for you?
No, yeah, but Dave answered that perfectly. I agree, yeah.
Okay, great. So we are getting to the end of the session. Actually, we passed the time that we estimate, but that's fine because the discussion are quite good. I always have a kind of wrap-up question from more kind of a mineral exploration point of view and more broad. So if you, each of you can say me in 1 minute, what is the main challenge on this type of deposits to find new discoveries? 1 minute each to give some thoughts on this.
Look, I think we've touched on this before. We have a fairly good but not complete understanding of what's happening within the ore bodies themselves. These are huge systems, okay? And very rarely do we see the edges of the systems. So we don't really know what's happening geochemically or mineralogically as we shift both laterally and vertically from these systems. So at the deposit scale, this level of knowledge has to be significantly increased. And then I would argue, I think Murray's pointed it out before, we don't know what's happening both vertically above and below the level of mineralization. We don't know what's happening with the aquifer geometry, the nature of alteration within the aquifer as we step away from the exposed basin margins, and we really have very little data about what's happening higher in the stratigraphy. So they're areas that we really need to try and infill.
Great. Koen? Yeah,
and to follow on from that, I suppose, is coming back to the question of scale, as to really understand a basin margin into a basin, and to understand the types of questions about what what are the units above the stratigraphy doing? You need, I don't know, something like 10, 20 kilometers of a research area. And the sort of problem that I see maybe is that when you look at the exploration licenses and the size of those, you could probably fit maybe 2 or 3 licenses within that scale. And so it is really almost above. So these questions are almost at a scale above the scale of an individual exploration license. And then obviously there will be bigger exploration licenses, but so it's almost like we would need a collaborative effort, I think, pulling together data, which is expensive to get sometimes, especially if you're looking at drilling, which is risky to get because who's going to drill into the unknown? And so maybe there's another discussion to be had there, and how do we actually make that work so that we can get the data? That's 1 minute of my thoughts.
Okay, so we really need to understand better before we think in new discoveries. Okay, I would like to thank you both for these great talks and for this discussion. And following a bit what we is talking here about geochemistry, I would like to invite you to the afternoon session where we will have some geochemical perspectives with James David, Philip Muches, and Nicholas Saintela, and we certainly continue some of this discussion on sediment-hosted copper deposits. And everyone, I will invite everyone to join in the afternoon. And I would like to say thank you again, Koen and Dave, Selley, and Halleluya for being here with me and for this great discussion on these sediment-hosted copper deposits.